In previous videos, we have looked at how to know if a function has an inverse. If our function is 1 to 1, meaning for every x input there is a unique y output, or if our function passes the horizontal line test, then our function has an inverse. Once we know our function has an inverse, our next goal is to find the inverse. The strategy here is to rearrange our equation such that we have x by itself. We add 1 and divide by 2 to reach a function that's now in terms of y. This is our inverse function. Don't forget, the textbook may ask you to write the inverse function in terms of x instead. Let's try another one. I undo division by multiplying both sides by 12. I undo addition by subtracting by 11. I undo multiplication by dividing both sides by 3. We then have a function in terms of y, that is our inverse function. Of course, the textbook may write the function in terms of x. Let's do one more. We change f of x to y, and then undo subtraction by adding 1 to both sides. Then I undo the exponent by... Wait, how do you undo the exponential function? We can solve for x as long as x is not in the exponent. So what we need is some sort of operation that brings that x down. This is where logarithms come in. If I take the logarithm of both sides of this function, I will be able to cancel out the base and bring down that x. Now I have found my inverse function. Notice how when I use the logarithm, I also added this little 2 here. This is because there is no one-size-fits-all for logs. If you want to undo an exponential function with a base of 2, you must use a logarithm of base of 2 as well. If you want to undo an exponential with base of 5, you must also use a log with base of 5 as well. If you want to undo a base of 121, then you must also use a log with base 121. Okay, I think you guys get the picture. That being said, to undo a log function, you must put the function in the exponent of the matching base. Meaning if I want to eliminate a log of base 2, I put both sides of the equation in the exponent of base 2. If I want to undo log with base 5, I put both sides of the equation in the exponent with the base of 5. The similar approach can be taken with log of base 121. Let's get some practice using these equivalencies. To undo a log base of 5, we had to put both sides of the equation into the exponent with the base of 5. Then, the base 5 and the log base 5 will cancel out, leaving us with just x on the right-hand side. Now we simplify. Now we want to take this exponential function and rewrite it in log form. First thing we have to do is take log base 12 of both sides. We choose a base of 12 because we want the exponential with the base of 12 to eventually cancel out. Now we simplify. The property we've used for the past couple of examples is called the inverse property, which states that if I take the log of an exponential with similar base, I'm left with whatever is in the parentheses. And if I take b raised to the log with base b, I am left with whatever is in the parentheses as well. Now let's talk about evaluating logs and the thought process that you should have. What I do is set my equation equal to an unknown value, and then use the inverse property. Now ask yourself, to what power do you have to raise 2 in order to get 16? 4. First, I write my statement with an unknown and then use the inverse property. So what do I have to raise 25 to get to 5? Well, if I take the square root of 25, it equals 5. So x has to equal 1/2. Well, we know that 7 squared is 49, but what I need here is 1/49. To put this number in the denominator, we raise it by a negative. Remember, an exponential function is always greater than 0 and not equal to 1. This means that the base of a logarithmic function must also be greater than 0 and not equal to 1. If you have forgotten this property of an exponential function, I recommend you revisiting these videos. Let's revisit the graph of an exponential function. Remember that the domain for an exponential function of this form is the entire real line, while the range of this function are all real numbers greater than 0. If you remember from the inverse video, we mentioned that the inverse of a function has a graph that is the graph of the original function, just flipped over the y equals x axis. We also stated that the domain and the range also switch for the inverse. So the domain of a log function of this form is the set of real numbers greater than 0, and the range would be the entire set of real numbers. Of course, not all logarithms are given in this simple form, so we must be able to find the domain of more complex logarithms. Luckily, it's still not too complicated. Remember how we evaluated a logarithm? Well, we could think of this part as the base of an exponential, and this part as the output of an exponential. Since the output of an exponential must be greater than 0, we can say that the domain of a logarithmic function are the numbers that make whatever is inside this parentheses greater than 0. The last thing I want to mention for this video is some special notation you will see. A log base of 10 is simplified as just log. This is the same log that you see on your calculator. When you click the log button on your calculator, they don't ask you what base you want. They automatically assume that you want to use log base 10. The other special notation is if the base is Euler's number, e. This was introduced in the last video. If this is the case, they call a function not log base e, but the natural log, and it's denoted by ln. So if you want to get rid of an exponential with base e, you will use the ln function on the calculator. Remember, these are just arbitrary notations. It doesn't change the way the logarithms actually work.